When looking at normal curves, there are actually two different ways to determine if a data point is an outlier. So just a quick reminder, outliers are values that sort of fall outside of normal. So these would be sort of the exceptions to the rule. Now, when it comes to normal distributions, our general rule of thumb is that anything within 2 standard deviations of that mean is going to be normal. That's 95% of all the data, which means anything that falls above or below that is going to be our outliers. So, in this case, these are my outliers in red. And then anything in the middle here, you're good, you're normal. So when it comes to justifying whether or not values are outliers, we're going to try and move away from it just looks like it and use some sort of data to back it up. Now, one option is to just use the normal curve. If you have a normal curve graphed out and you know exactly what's 2 standard deviations above or below the mean, then you can clearly state, well, that point just doesn't fall within 2 standard deviations of the mean. It must be an outlier. Great. But let's say I don't have a full normal curve shown out. I can use something known as a z-score. Basically, what a z-score does is it tells you how many standard deviations above or below a value is away from the mean. So it's sort of telling you, okay, we're this many standard deviations away. So if your z-score is less than -2, so like -2.5, that would tell me that my data point is 2.5 standard deviations below the mean. So it would be an outlier. Just as if the z-score was more than 2, that would tell me it's like 2.1. Then it's 2.1 standard deviations above the mean, also an outlier. So these are going to be sort of the key to know whether or not my point is an outlier using z-scores. So we're going to do an example, still going with that SAT data, and we're going to look at how we could justify an outlier with just using the normal curve and how could we justify using z-scores. So we're going to start with the normal curve one because we've already drawn a normal curve for this situation, and then we'll move into the z-scores. So we have a score of 1500. Is it an outlier? Justify your answer. So if I go and I think about my normal curve in this situation, and I'm going to just sort of resketch a small picture here. I had 1060 as my mean, 1277, and then 1494 was 2 standard deviations above. So 1500 would fall somewhere like here. That would be 1500. And so clearly 1500 is above 2 standard deviations away. Now I have to take that and put it into words so that I am explaining my reasoning to others in a way that they understand. So I might say, since 1494 is 2 standard deviations above the mean, and 1500 is above that value, a score of 1500 would be an outlier. So that's one way to explain it. Now let's say I hadn't already done the math to figure out what was 2 standard deviations above. A z-score method actually gives you a really quick way to sort of figure out where is that 1500 in terms of my normal curve. And so if I would show out my z-score calculations. And what it is it's taking the data value, that 1500, you subtract the mean, and then you divide by the standard deviation. So it's sort of like I'm looking between the distance between my two data points, and then how many times does the standard deviation fit into that. And in this case, I would get 2.028. So what this number tells me is that 1,500 is 2.028 standard deviations above the mean, which is more than 2, therefore an outlier. So 1,500 is an outlier because it lies 2.028 standard deviations above the mean, which is more than 2 standard deviations. So, it falls in that red outlier zone. Woohoo. And so that's a sort of general sense of how I can figure out if a number is an outlier. Now, the one last thing that we're going to be able to do with our normal curves is we can take a percentile and then get it back to a data point value. We're sort of working backwards from what we did. So let's say an average student at ASU has an SAT score that falls, not that typo, within the 75th percentile. Basically what that means is that 75% of the scores are below it. What SAT score would this student have? So if we go back to our Desmos graph, we're going to do a little bit of math. I could try and guess my way to a maximum score here, but that would be a little tedious. So I'm going to actually use one of my functions here. So if you go in and go back down to the distributions, you're going to see something that says inverse CDF. Because if you remember looking back up at the original problem, the original curve information, cumulative probability, the CDF, was what gave us the percentage. So an inverse means we want to work backwards. Now you'll notice if I just type that in, I get a question mark or an exclamation mark because it has a problem. I need a normal curve information here, which is why I named my normal curve above. So notice I named mine A. So if I type A and then, period. There it is, sorry. A period. That's going to allow me to then type something in. And then we said 75th percentile. So I type in my percent as a decimal and it undoes it. So a score of 1,206. And you could double check that. If I go over here and I type 1206, you'll notice I get about 75%. And so the inverse CDF allows me to sort of do that. So I'm going to go over here and I'm going to make a note. I'm going to be using Desmos. And I put the name dot, and then it was inverse CDF, and then the percent. So this is what I entered into my Desmos calculator. And it output 1206, what was that, 1206.36. Now, in the case of SAT scores, you can't have decimal answers, so we would call that a 1206 as my value. All right, that's really it for normal curves. The key is to sort of practice, play with it, answer a few questions, and sort of until you get the hang of how to use the tool and how we interpret the data. But in the end, this tool gives us a really easy way to make generalizations about data that's sort of equally distributed on either side of that mean value.